an interstellar object dubbed 3I/Atlas barrels into our solar system, heading straight for Mars at velocities and with materials never encountered previously. Scientists worldwide are stunned. It bears a cargo loaded with carbon dioxide, roughly eightfold its water volume, drawing near Mars from 30 million kilometers away as our planet remains obscured by solar glare. Meanwhile, NASA's Martian explorers detect possible signs of biological activity in the long-dried river channels of Jezero Crater. Could this be mere chance in the universe, a routine influx of rare frozen substances, or perhaps a deliberate construct? That's the true mission of 3I/Atlas close to the Red Planet. What unfolds afterward might transform our understanding of Mars and the broader field of interstellar exploration. 3I/Atlas stands apart from ordinary comets. Its trajectory slices through the solar system on a hyperbolic path, boasting an eccentricity exceeding 1, a clear indicator of origins outside the Sun's gravitational pull. Experts verified this mere hours after spotting it on July 1, 2025, when orbital computations revealed it won't circle back. Rather than orbiting like planets or typical icy wanderers, 3I/Atlas hurtles onward in a single pass, clocking nearly 68 kilometers per second. That's roughly 150,000 miles per hour, outpacing anything originating within our cosmic neighborhood. Its nearest pass by Earth arrives at 1.8 astronomical units, or around 269 million kilometers, come December 2025. Yet even from afar, it captivates for a distinct feature: the luminous envelope, or coma, encircling its frozen nucleus. Sunlight warms a comet, triggering the release of solidified vapors and particles that create this hazy aura, and occasionally a trailing tail. Conventional comets follow the dirty snowball archetype, rich in water vapor above all. Initial spectral readings from 3I/Atlas, however, reveal an atypical mix, with carbon dioxide dominating over water by a wide margin. This defies expectations for standard comets. Long-standing theories, built on years of data, predict water ice as the primary component, laced with lesser traces of carbon dioxide and other volatiles. In this case, the proportions are inverted. The coma's makeup suggests formation in a far chillier, more remote setting than anything our solar system could foster. As 3I/Atlas surges closer, its actions compel researchers to re-evaluate foundational principles of cometary makeup and motion. Together, its velocity, course, and odd envelope point to an authentic outsider from another stellar domain, potentially harboring clues to alien cosmic evolution. Jezero Crater guards its enigmas within accumulated deposits on Mars. Eon's back, a waterway etched through the planet's crust, fanning into a vast delta. There, fine muds and clays accumulated, sealing in remnants of any biology or reactions that graced this prehistoric flow. Amid the remnants, experts have focused on an intriguing anomaly: rounded, mottled areas dotting the delta, termed leopard spot textures. These formations ignited fierce debates upon their debut in detailed imagery, with certain specialists proposing they represent biosignatures, tangible evidence of past microbial thriving on Mars. Dr. Hiroshi Tanaka, a seasoned analyst of planetary soils, urges restraint before declaring victories. He notes that terrestrial river fans act as natural archives for carbon-based materials. Their powdery layers shield delicate substances from surface rigors. On Mars, with its sparse atmosphere and relentless cosmic rays, spots like Jezero's delta rank among the top sites for safeguarding primordial organics. Still, not all peculiarities signal vitality. Dr. Tanaka's group has demonstrated that comparable markings arise from inorganic processes, crystal development, or gradual erosion of stone. Mars research faces the puzzle of distinguishing native features from extraterrestrial imports. A formation such as Jezero's serves as an ideal snare. It captures carbon compounds, be they born in local pools or wafted in via micrometeorites and frosts from the void. With fresh assertions of biosignatures emerging, the chance for misinterpretation rises. The arrival of 3I/Atlas near Mars at this juncture intensifies the inquiry. Should novel organic traces surface in the delta, Do they echo the world's ancient chronicle or signal a recent cosmic gift? Revelations hide in the strata, poised for meticulous analysis to uncover. A comet's molecular profile typically betrays its genesis. For years, stargazers have gauged the interplay of water, steam, and carbon dioxide in cometary auras, leveraging these proportions to trace ice formation across cosmic timescales. Yet, 3I/Atlas disrupts established norms. On July 18, 2025, the Gran Telescopio Canarias captured a carbon dioxide to water proportion approaching 8:1, a stark deviation. Typical comets, including those from our system's icy fringes, feature water in excess of carbon dioxide. Here, the dynamic shifts dramatically. Controversy ignited the moment findings appeared on preprint platforms. Certain groups immediately floated the possibility the potential for a calibration error in the readings has been largely dismissed. Our planet's atmosphere is laden with carbon dioxide, making it challenging to isolate those spectral lines from a dim object originating from another star system. However, subsequent observations using the Keck Observatory and the Nordic Optical Telescope confirmed the unusual feature. Even the most conservative ratios, around 5:1, deviate significantly from typical values. Now, scientists are debating if this signals the comet's birth in an atypical molecular cloud or indicates intense alteration from interstellar radiation over its extended voyage. Complicating matters further, experts detected a greenish hue in the spectrum of its coma. This emission stems from substances such as dicarbon and cyanide, which fluoresce vividly under vigorous chemical reactions. In 3I/Atlas, their prominence seems elevated, perhaps driven by the same CO2 heavy emissions that distinguish it. Certain specialists propose this implies formation past the conventional water-ice boundary, in a zone where CO2 solidifies initially. Alternatives include preferential vaporization or radiation degrading intricate ices to liberate uncommon compounds. Each fresh dataset deepens the enigma, as time runs short for Martian probes to snag definitive readings before the visitor fades from view. The approach to October 3rd has turned into a frantic pursuit. On that date, 3I/Atlas will glide by Mars at a mere 0.19 Australian dollars, roughly 28 million kilometers away. In the grand scale of the cosmos, that's incredibly close, particularly for something hailing from a distant stellar neighborhood. Yet, the nearest passage introduces a snag. From our vantage point, Mars and 3I/Atlas will align almost straight behind the Sun. For several weeks before and after the encounter, intense solar glare will overwhelm the view, compelling Earthbound scopes to close up and pause operations. This solar conjunction, spanning from late September to late October, imposes a total observational void. Premier facilities like Keck, VLT, and JWST will be unable to monitor the comet or Mars atmosphere. Radio connections to Martian satellites will falter too, overwhelmed by solar interference. The schedule offers no mercy. The flyby's alignment positions the prime window for spotting any interplay between 3I/Atlas and Mars right in the heart of this observational blackout. Such alignments are infrequent. Estimates suggest the likelihood of an interstellar intruder coming this near Mars amid a conjunction is about 1 in 100 annually, drawing from models of extrasolar visitors and orbital configurations. To those studying worlds, it resembles a taunt from the stars. Decade's most captivating interloper, arriving just as it evades the solar system's sole world with ongoing searches for signs of life, while observers on Earth must avert their gaze. As the communications hiatus looms, focus turns to the sparse sentinels still active. Preset automated protocols on Mars satellites will provide the sole means to gather intel during the pass. Teams are racing to optimize every available slot prior to the cutoff. No second chances exist, and each batch of info might unlock the secrets. Time presses on, indifferent to human endeavors. With 3I/Atlas hurtling toward the rusty world, orbital craft stand as the final observers. Key players include ESA's Mars Express and the ExoMars Trace Gas Orbiter, both now primed to record any traces possible before access ends. Dr. Colin Frank Wilson, Mars Express project scientist, calls this venture an exceptional research wager, unlikely to repeat this decade. The high-resolution stereo camera, HRSC, on Mars Express excels at detailed terrain imaging. Its spectral bands cover 380 to 1,000 nanometers. Yet from 28 million kilometers out, 3I/Atlas will appear as a mere speck. At roughly 128,000 kilometers per pixel, the coma and core will merge into one indistinct blob. Solely a sudden, intense flare from the comet might allow HRSC to glimpse its form or dimensions. Prospects are low, yet feasible. The NOMAD spectrometer on the Trace Gas Orbiter employs a contrasting method. Its UV and IR detectors are calibrated for spotting CO2 and water vapor, the very elements marking 3I/Atlas. Conceptually, a robust venting episode might imprint a detectable signature in NOMAD's logs. Its prowess in pinpointing Martian atmospheric traces hits parts per billion levels for select gases. Still, for such a remote, subdued source, the emission needs to surpass ambient interference. This tests the limits of the device's capabilities. Each satellite contends with logistical barriers. Amid conjunction, Earth contact becomes sporadic or non-existent. Gear operates via autonomous sequences, with there's no room for 11th-hour tweaks. Information gathered amid this communications blackout could linger in the spacecraft's internal storage for weeks, potentially getting overwritten if the buffers overflow prior to downlink restoration. The anticipated luminosity of the comet, teetering around magnitude 17 or 18, stretches the imaging sensors to their utmost capabilities. Instruments like HRSC and KSSGS could potentially snag a faint point of light. Omega and Spica stand an even slimmer chance of picking up more than a barely perceptible shimmer. Dr. Wilson and his team have weighed options for optimizing these invaluable viewing windows. They're fully aware of the slim prospects. Barring an unforeseen flare-up from 3I/Atlas that catches everyone off guard, the probable result will be a series of detection thresholds, readings that merely indicate what evaded capture. Yet such boundaries hold value. A surge in carbon dioxide or an anomalous spectral feature would ignite a frenzy to scrutinize each image anew, hunting for the truly extraordinary. A sharp shift in emissions, an unusual compound, or a novel type of dust particle all hinge on the precision and fortune of these satellites. At present, the wisest approach involves monitoring, logging, and preparing to analyze anything the hardware manages to record. The cosmos has presented Mars satellites with an extraordinary mission, and they're hurrying to fulfill it, regardless of how dim the trace. Conjecture surrounding 3I/Atlas branches into three primary theories. The initial one views the comet's near approach to Mars as an uncommon yet ordinary occurrence. Models of interstellar visitor rates indicate that an object of this scale draws within 0.2 astronomical units of Mars roughly once every 50 to 200 years. This translates to yearly probabilities ranging from 1 in 100 to 1 in 200. A slim possibility, yet well within the bounds of probability. Many experts regard it as a mere fluctuation in statistics, a nudge that chance can mimic designs we might overinterpret. The next hypothesis draws on long-standing visions of planetary engineering. Might 3I/Atlas serve as a deliberate payload directed toward Mars? Its composition raises eyebrows. An 8:1 proportion of carbon dioxide to water, a verdant hue suggesting active compounds, and a trajectory grazing Mars right amid buzz over potential life indicators. For this idea to stand, proof of intentional control would be essential. An irregular plume, a synthetic mix of isotopes, or an orbital alteration defying gravitational pulls or routine venting. The path follows a hyperbolic arc. No evidence emerges of extra forces at play, and the absence of transmissions eliminates blatant transmissions. Nevertheless, the orbiters remain vigilant for irregularities. Elevated levels of scarce isotopes, a rapid gas ejection, or particles bearing strange compositions. The final path explores panspermia, the notion that life's precursors travel interstellar distances. Should the comet's envelope harbor intricate organic materials, or if ratios in its debris mirror those in meteoroids or primordial Martian samples, it might bolster the concept. However, validating panspermia proves daunting. A mere uptick in organics near the encounter falls short. Researchers will seek distinctive isotopic signatures, proportions of carbon, nitrogen, and oxygen mismatched with local or solar origins. Solely then might random alignment be dismissed. Every hypothesis establishes its evidentiary threshold. Currently, natural causes lead the pack, though the quest for the unconventional persists. Whispers about 3I/Atlas have proliferated as swiftly as the body itself, stoked by viral jests on stellar timers and assertions of crafted shipments. In the realm of science, bold narratives require ironclad proof. Still, the roots of its elevated carbon dioxide levels and ties to Mars life detection research linger unanswered. Current findings offer no backing for human-made meddling, yet they enrich insights into cosmic compositions and the hurdles of decoding world oddities. 3I/Atlas's proximity to Mars forms a scarce cosmic trial, one poised to challenge our instruments, our doubt, and our skill at distinguishing genuine hints from clutter in the pursuit of extraterrestrial biology.